Okay, we are recording. Projector looks like it's up and running, which means we can get started on working. All right, today we start chapter 21. Circuits and DC instruments. We have 6 sections. We're going to learn some more of the particulars about how electricity is used, practically speaking. And this will be our last chapter before the exam, which will cover chapters 18, 19, 20, and 21. And then we'll move on to magnetism and electromagnetism. And let's see. Then after that we move to optics, light, and modern physics. And essentially that's about the time when we get to optics, light, and modern physics. That's that downturn where we get to relax a little bit, where it's not quite so mathematical. When we get to particularly to the modern physics part of this class, we just don't have enough math background to cover it deeply, so we just kind of touch on it here and there and look at some cool stuff and do some simple calculations and some simple applications, but we're just learning about what's going on in physics today, or at least the past 100 years. Modern physics is everything since 1905. Ever since Einstein published his 5 papers in 1905, we consider everything after that to be modern physics. So we will, that will be about the last quarter to a third of our class. And so we're moving along here. We've gotten through the first quarter or third-ish, and now we're moving forward. So 21 is where we're at today. I love this picture because it's got a little mix of both the old and the new. It's got these old CRT monitors made by IBM. It's got some flat screens in the back here, which we're more familiar with these days. But this is certainly a few years old, this picture. Of course, computers are, usually when we talk about electronics, we're always thinking about things like computers, but electronics are much more varied than just computers. There are many more things out there that are nothing like a computer, but are considered electronics, of course. And remember, we talked about resistors. So we talked about a resistance and resistors already, but a resistor is a particular type of material that is designed to have usually a fairly high resistance, to resist the flow of current, in other words, is what it does. So as current encounters a resistor, the resistor literally slows it down and doesn't allow the current to flow through as quickly as it might want to. And we have lots of different ways that we can connect resistors. The most common ways that we can connect resistors are to connect them in in series, one right after the other, 1, 2, 3, 4, where the end of one resistor is connected to the beginning of the next, and so on and so forth. But it's important to know that when you have resistors in series, you can't have any branches off in between anywhere. Resistors are only in series if they look just like this in the circuit diagram. This is the symbol for a resistor in circuit diagramming, and just a straight line is the symbol for a wire, which is considered to have very low or zero resistance in circuits. So if you put them right in a row without any things branching off anywhere, then they are considered to be in series. Whereas these ones are considered to be in parallel. You might guess why, because they look like they're parallel lines. 1, 2, 3, 4 resistors in parallel. And when you have resistors in parallel, you must have one side of the resistor connected to one side of the other resistor, and on the other sides they must be connected. Both sides must be connected to each other directly. There cannot be anything in between that connection. So you should be able to leave one resistor and go to the other resistor without ever going through another component. It's just traveling along a wire to another one, and you should be able to do that on both sides. And if you can do that on both sides, then it's in parallel with that other resistor. And if you can do it on both sides with 3 resistors, like this one with 3 other resistors, you can connect them without any problem. Then they're in parallel. Then all 4 of them are in parallel with each other. So those are 2 very simple ways that resistors can be connected to each other. There are other things that you can do as well. There are ways to connect resistors so that they're neither in parallel nor in series. But we'll get to that later. So, another way to think of this is in terms of flow of charge or flow of current. How do you know resistors are in series? Well, if the flow of current must go through each resistor because there's no other path for it to go, then you know that those resistors that current must go through are in series. So in this case, you have 1, 2, 3 resistors all lined up in a row, and the current leaves the battery and it goes out here and it goes through this first resistor, and then it goes to the next resistor, and there was nowhere else for it to go. The current can't just jump out of the circuit. There has to be a wire for it to travel along, and so it can't go anywhere. It has to go through the second resistor. There's no other path for it to go through, so it has to go through the third resistor. So the resistors 1, 2, and 3 are in series. And that's how we know, is because the current had nowhere else to go. It had to go through 1, then 2, then 3, without any divergence. And when that is the case, you have resistors in series. You can actually represent them as a single resistor. They behave as a single resistor. It's just, you could just say, well, those 3 resistors are like having just one resistor. However, what would the value of that resistor be? Because each resistor has a value measured in ohms, just like we calculated the resistance of wires and cables and other things in the previous chapter. The resistance of a resistor is measured in ohms. Excuse me. So what would be the resistance of the replacement resistor, or what we usually call this the equivalent resistor in series? Well, one of the things that we can do is we can say we know that the voltage difference from this side of the battery to this side of the battery is the voltage difference of the battery. And that, since those 2 sides are connected to either side of these series of resistors, then the voltage difference all the way across these resistors is the voltage difference of the battery. Seems a little bit simple, but it's just an important thing to realize. So we can say that the voltage across the first resistor plus the voltage across the second resistor plus the voltage across the third resistor equals the voltage across the battery. And using Ohm's law, each of these voltages equal to the current times the resistance, current times resistance 1, current times resistance 2, current times resistance 3, where all the currents are the same because the current has to pass through all 3 of them. It has nowhere else to go, so it must be the same passing through all 3. And when we do that, right here, when we do that, current times resistance, current times resistance, current times resistance, then we can say that the current times the sum of the resistances is going to be the total current times the total resistance, because now we've essentially algebraically shown this. So what that means is that this R1 plus R2 plus R3 is equal to the total resistance in series. So it makes it quite simple. If you have resistors that are in series, like this, whatever else, the resistors just add up, 1, 2, 3. Just add the first resistance to the second resistance to the third resistance, and that's your total resistance for that set of resistors. It's very simple when the resistors are in series. Another way you can think of it is that resistance from our last chapter was dependent on distance, the length of the resistor, and the cross-sectional area, and the material of the resistor. So if you just have a longer resistor and more material there and everything else, it's just going to add on to the resistor. It's just like making a longer resistor, so it just makes more resistance. Just add them together. Simple as that. However, it's not going to be always so simple. Here's an example where they have a resistance, three resistors, 1 ohm, 6 ohms, and 13 ohms. They put them in series. What is the total resistance? You just add those three numbers together, you get 20 ohms total resistance. And once you know the total resistance in the circuit, so this would be like this picture here, resistance 1, resistance 2, resistance 3. Once you know the total resistance of the circuit, because you've added them up and replaced these three resistors with one resistor, then you can use Ohm's law very simply to calculate the current. You know the voltage, you know the total resistance, you can calculate the current going through the total circuit, and once you know that current, you can calculate all kinds of things. So we use Ohm's law to calculate the current going through the circuit, and then we use that current with each resistor to calculate the voltage drop across each resistor. So current times resistance 1 gives us the voltage across resistor 1, turns out to be 0.6 volts. Current times resistor 2 equals voltage 2, which gives us 3.6 volts across the second resistor. Current times resistance 3 gives us voltage 3, which is the voltage across the third resistor. And notice that for the same current, since they all have 0.6 amps going through them, 0.6, 0.6, 0.6 amps, the voltage drop, or the change in voltage across each resistor, is directly proportional to the resistance. A 1 ohm resistor has a small amount of voltage compared to a 6 ohm resistor. The 6 ohm resistor gets a much different, in fact the 6 ohm resistor gets 6 times as much voltage drop. And the 13 ohm resistor gets 13 times as much voltage drop as the 1 ohm resistor. So it is directly proportional to the resistance, and that the proportionality is the proportionality constant is that constant current going through all resistors. Then if you add those voltages together, just like we thought, you will get a total of 12 volts, which is what the battery is providing. The battery is providing that potential difference of 12 volts. Once you have that voltage across each resistor and the current, since it's all the same going through each resistor, you can use I squared R for each resistor to figure out how much power is dissipated by each resistor. Each resistor is going to heat up and it's going to take energy out of the circuit. It's going to remove energy from the circuit. That's how it slows down the current, is by removing energy from the current. And so as the current goes through the first resistor, it loses 0.360 watts of power. As it goes through the second, it loses the second one obviously is going to heat up more. It's going to give off more heat, 2.16 watts. The last one will heat up the most at 4.68 watts. So, what if they're in parallel? In parallel, it's not so simple. In parallel, you have a current leaving the battery and comes here to this first branch where it has two choices. It can keep going straight or it can go down through the first resistor. And it does both. Some of the current keeps going straight, some of it goes down through the first resistor. And then when it gets to the second resistor, it has another choice. Some of it can go straight, some of it can go through the second resistor. And so on. It can go through the third resistor. And once the current gets around, it actually even has a choice when it gets this, when it comes this way. When it comes around the other side, it could keep going straight or go up this way, or it could keep going straight and go up this way. And it kind of depends on what's going on in the circuit. It depends on what the circuit is like. If the resistors are truly in parallel, so that each side of each resistor is connected directly to each side of the other side as well, so both sides of all resistors that are in parallel are connected to each other, and there is nothing in between. There can't be a resistor here, there can't be a battery here or anything else. There's nothing in between those connections. Then they are in parallel. And when they are in parallel, we can actually calculate what their resistance is and make a total resistance in parallel, R sub P they call it. We often call it equivalent resistance again for these three resistors. But it's going to be a bit different. Why is it going to be a bit different? Because the current splits. When we're talking about those resistors in series, you could think of this resistors in series as kind of like rapids on a river, one after the other, after the other, after the other. We have big rocks sticking into the river and other things that are slowing down the river, turns in the river, things that slow down the river, one thing slowing it down after another thing slowing it down. and it slows down the river more and more and more every time. But when you have resistors in parallel, it's like you're coming down the river here from this B letter, and then all of a sudden the river splits into 4 rivers. And each river has a rapids, but it's splitting into 4 rivers. What's going to happen then? What happens then is the river actually can flow a little bit faster, right? Because it can split up, it can take different paths, it'll pick the rapids. Most of the water will go to the rapids that has the least rocks and the biggest space and all this, the least resistance, in other words. So the path that's chosen is always the path of least resistance, right? That is not some poetic thing, that's actually a physics thing, right? The path of least resistance is taken by electricity. It likes to go down that path of least resistance, so most of the current will go there, and the least current will go down the path of most resistance, and you'll end up with actually a total resistance that is less than your overall resistance. It'll be less than your smallest resistor that you have in parallel. And let's see how that works out mathematically. Here they show how a house is wired. Houses are wired in parallel for 2 reasons. First, because you want lower resistance so you can get good current. If you wire your house in parallel, you get good current. But the other reason that you wire everything in parallel in your house is when you wire things in series and one of your resistors breaks, like if one of your light bulbs went out, it breaks the circuit everywhere. And so the current can't flow. So if you had your house wired in series and you blew one light bulb, every other thing in the house would turn off. So we wire our houses in parallel so that we can have a light bulb burn out, but it doesn't burn anything. It doesn't turn anything else off at the same time. Well, the one thing that we know about current in parallel circuits is that the current going through each resistor, or going down each rapid in that river, each one of those currents has to add up to the total current because it splits into these currents, right? You still get conservation of current in the end. And so we have an equation that looks like this. I equals I1 plus I2 plus I3 instead of the voltage equation we had with our resistors in series. If this is the case, then we go ahead and replace I with V over R using Ohm's law. V over R1 for I1, V over R2 for R2, and V over R3 for I3. And why do we keep the voltages the same? Well, because in a parallel circuit, and when resistors are in parallel, they're all connected to the same side of the battery on one side, and they're all connected to the other side of the battery on the other side. So the voltage across them is the voltage of the battery, or the voltage that is there, whatever it is. So we can go ahead and say that the voltage is the same, V, whatever the voltage is, it's the same. Then we can factor out that V, and our current equals V times 1 over the resistance in parallel. We have this 1 over relationship now. And what that tells us in the end is that the 1 over the equivalent resistance is equal to 1 over R1 plus 1 over R2 plus 1 over R3 and so on. So what you have to do is you have to calculate 1 over R2 and 1 over R2, 1 over R1 and then 1 over R2 and then 1 over R3 until you've got all your resistors in parallel. Add all those 1 over R things together, and then you have to take the inverse of that answer to get your RP, because that's equal to 1 over RP, right? So let's take a look at this example where we do this. We have the voltage output of the battery above. We have 3 resistors, and they tell us the 3 resistances. Resistance 1 ohm, 6 ohms, and 13 ohms, just like the previous example. We're going to use a 12-volt battery again. And we want to know the total resistance. So here's the formula. We plug it in, 1 over 1, 1 over 6, and 1 over 13 ohms. We figure out those. If you really want to do a common denominator and add them up, you can. I just use a calculator. But in the end, you're going to get a value for 1 over the equivalent resistance, or 1 over the resistance in parallel, equal to 1.2436 divided by ohms. So this is not a resistance. You don't divide by ohms to get a resistance. It would be ohms. So in order to get a resistance, we need to turn this on its head. 1 over this number. 1 over 1.2436 times ohms is correct. And you get 0.8041 ohms. And what we said before when we were talking about the river analogy is that the total resistance should be smaller than the smallest resistor, and it is. 0.8 is smaller than 1, which was the smallest resistor we started with. So whenever you're calculating resistances in series, if you get something that is more than your smallest resistor that's in parallel. I did it again. Whenever you're calculating resistances in parallel, if you get an answer for your total resistance of the resistors that are in parallel that is greater than your smallest resistor, you know you're wrong. Got to go back and fix it. This number was definitely wrong. It was greater than 1, so we finished the problem, took 1 over that number, and we got 0.8. That is less than 1, so that is a viable answer. That answer is doable. So here's the question. You have two 500 ohm resistors and you want to make a 250 ohm resistor. How do you do it? Put them in parallel. Simple. If you have two 500 ohm resistors in parallel, you get 1 over 500 plus 1 over 500, right? That gives you 2 over 500. And then if you invert that, it gives you 500 over 2, which is 250. So two equivalent resistors in parallel give you half one of those resistors for a total resistance, right? It's a quick way to create a resistance you didn't have before. If you're really good, you can be given any set of resistors and you can make any resistance you need, really. And if you look at circuit boards, so let's look at a complex circuit board. Circuit board is just a piece of usually fiberglass that's got a bunch of electronic components on it. So here's a nice picture of a circuit board. You can see there's lots and lots of things on this. And pretty much every single one of these tiny little black dots on here that has little pieces of silver on either side, each one of those things is a resistor. If it's a golden one like this, like a yellow, that's a capacitor. Those are all capacitors, but all the black ones, almost every single little tiny black thing on there, and they are tiny. They're like 1 millimeter by 2 millimeters. They're itty bitty. Every single one of those is a resistor if it just has a silver thing on each side. The silver thing on each side is essentially the wire that's connecting it to the board. So there are just hundreds of resistors on this board, and then you're not even seeing the whole board, you're just seeing part of it. Excuse me, and that doesn't even count the resistors that are inside of these chips. And that's just one side of the board. These boards are often double-sided. This one almost certainly is. And sometimes they're even triple-sided, if you can imagine that. Sometimes they even have an interior layer of circuitry. So any circuit board you look at, you can see, here's a nice zoomed in version. This is probably, 10 times magnification. So here's, and they actually even put numbers on them here so that you can know how big the resistance is. This resistor here, this one here, this one here. It's not necessarily the actual number of the resistance, it's kind of a code, but anything that has more than one silver thing connecting it is usually some other kind of device. But if it just has one thing on each side, here that's a resistor, that's a resistor, 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 resistor. There's lots and lots of resistors. And resistors come in all shapes and sizes. Those are what we call surface mount resistors, but there are other types of resistors that are much different than that. Let's see if I can find you, no, not on that board. Sometimes you have to have a bigger resistor. So here is a bigger resistor. This is a standard, what we call carbon film resistor right here. It uses stripes on it for a code to tell you what size the resistance is. There's another one, another carbon film resistor that one actually might be a wire wound, but here's another kind of a resistor right here. This resistor right here is actually, and there you can see there's 3 of them here. These are actually variable resistors. So you put a little screwdriver in there and you can turn the resistor and it changes the resistance. You can increase or decrease it. Let's see what other resistors they have for us here. There are really big resistors we call load resistors or power resistors. And these ones give off so much heat, they actually have a heat sink built into them. So this whole thing on the outside is made of aluminum, has veins on it, and you bolt it down to something that's metal so that it'll carry away the heat. Some of them are smaller. You have these ones which are smaller, but they're encased in this material to help carry away the heat. These are power resistors, and they come in all kinds of shapes and sizes. Some of them are so big. These are the kinds of resistors you might see at a power plant. They allow wind and air and rain to go through them so that they can cool off. Here's a power resistor that uses a different kind of heat sink. Here, this one has a hole through the middle so that air can go through it and cool it off. So resistor, and some of these, can be the size of a building. This one is enclosed in a box, probably with fans on it to try to keep it cool as they dissipate so much heat. Here's a variable resistor that we call rheostat. It's also a power resistor. You slide this slide along and it changes the resistance of it. Here's another slide resistor that changes, you can change the resistance of. So there's different kinds of power resistors. I've got some of these. These are just this essentially is just a long wire wrapped around and around and around and around a tube, and got a connector on each end. And that's another type of power resistor. Just so many different kinds of resistors out there. Resistors are used in everything. They're just the most common, simple, and very important electrical component. So once you've figured out once you figured out your equivalent resistance for resistors in parallel, you can do the same things that you did before with the resistors in series. You can calculate the current. So you take the total, it'll give you the total current going through the whole thing. But then you can also calculate the current going through each resistor. Because remember, the current is different. So this tells you the total current going through the system from one end of the battery to the other end of the battery. But this one will tell you the current going through each individual resistor. And you see that the 1 ohm resistor has 12 amps of current. The 6 ohm resistor has 2 amps of current. The 13 ohm, 0.92. Did the current take the path of least resistance? It absolutely did, right? The current, most of it went through, there's 14.92 amps, and 12 amps of it went through the 1 ohm resistor, which is what we would expect. That's the path that had least resistance. It just rushed that way and said, yeah, woohoo, I'm home free. Some of it actually was forced to go down the 6 ohm path, and a little bit of it had to go down the 13 ohm path just to make it all work out. But when you add all those together, you do get the total current, which is 14.92 amps. And you can calculate the power as well. In this case, we'll use voltage squared over R. It doesn't really matter what you use, since we've got the current and the voltage and everything else. We can use whatever we want. But they use voltage squared over R to get the current, the powers here. You can do that. You can also do power equals I times V. It'll also work. But in the end, you get the current through each resistor, or the power each resistor dissipates. And in this case, the 1 ohm resistor now dissipates the most power because it has the most current going through it, right? I think in the last one we saw differently, right? The biggest resistor had the most power going through it in series, but in parallel, the smallest resistor has the most power going through it. And why do you care about how much power is going through a resistor? Here's the power. Well, because that determines what type of resistor you need to use. If you have 144 watts of power going through your resistor, you need one of those big resistors that has the aluminum on it. Okay, I have a resistor in my back room that's a big power resistor, and it can handle like, I don't know, 100 watts or something, and that thing is a foot long. And it has a huge, I mean, it doesn't have that much resistance, it has a huge amount of air, flow and heat sinking capability. 144 watts is a lot of power. That's a lot of heat. That's a hot, bright light bulb. You wouldn't be able to touch the resistor, it would be so hot. So you have to be able to get that heat off of the resistor, because if it gets too hot, of course, it might melt. Things melt when they get hot. So you have to choose your resistor by how much power is going to go through it. And that's why we learn to do these calculations. No matter how you calculate the power, whatever equation you use, you will get the same powers through each resistor, and you will get the same total power. You can calculate using I times V, or V squared over R, or I squared times R, either way, any way you want. It will work since we have all those things. In reality, in a circuit, you're going to have pretty complex wiring. You're going to have all kinds of resistors in parallel, all kinds of resistors in series, and some resistors that don't appear to be in parallel or series but are, and some that appear to be in parallel or series but aren't. Okay, so you have all kinds of things, and you have to be careful on how you work with them. So in this circuit here, you can see obviously that these three resistors, 2, 3, and 4, are in parallel. And you can see obviously that 5 and 6 are in parallel. Right? But circuits are not always drawn obviously like this. Circuits are usually drawn by a computer. Circuit diagrams are usually drawn by a computer to save space on the paper, save space on the screen, so that you can get all the diagram into a space that you can read it. And so it's not always the most convenient for figuring out what's in parallel. Again, to figure out what's in parallel, go to the end of the resistor and see if you can follow a wire without passing through any other thing to another resistor. And if you can do that on both sides between the same two resistors, then those two are in parallel. If you cannot, they are not. Okay? And if you can do it for multiple resistors, then you have multiple resistors in parallel, just like these three are all in parallel. Then you can replace that with an equivalent resistance in parallel. And for this second set of resistors, you can replace that. So this circuit diagram, as long as you do the math right to get the equivalent resistance, is equal or equivalent to this diagram. In other words, these circuits will behave the same. The only difference is that in the middle of this circuit, the current is going to split 3 ways and then recombine, and split 2 ways and then recombine. And in this one, it wouldn't. But it would still behave the same as far as resistance, overall resistance is concerned, and current and everything else. So why would we do this? We would do this because this will help us to figure out what current is going through this circuit. If somebody just shows you this circuit and says, you know, this is the voltage, these are resistances, what's the current? You can't do it just by looking at this circuit. You have to break it down into a simple circuit that looks like a single voltage source and a single resistor if you can do it. And if you can do that, then you can figure out the current going through this resistor. Then you can figure out going through this, and then you can work backwards to figure out the current going through all the resistors until eventually you know the current going through every single resistor. And then you can know what kind of resistors to choose. Then you can know what the circuit is going to do. Then you can know all the things you want to know about the circuit. So we do this breaking down of circuits or simplifying of circuits by looking for things in parallel, replacing them, doing some calculations, and then looking for things in series, replacing them, doing some calculations, and doing that back and forth until we make a very simple circuit.
Like that one, you need to measure resistance of every single resistor in the voltage, and you can figure it out.
That's right. If you knew all the resistances here, then you could create an equivalent resistance for these three and replace it right here. Put a new number here that replaces these three. The same with this. So you have 2 new resistors and make a new circuit that represents this old circuit in the same resistive way, just simpler. And then since now these two are obviously in series, remember you're in series, if you go through one resistor and then go through the next resistor without anything in between, no branches in between, can't be a branch off in some direction, no elements in between, if they're just lined up one after the other with nothing in between except a wire, one single wire, no branching wires, then they are in series, right? Then you can add them together just simply, 1 ohm plus 5 ohms or whatever. And that makes a resistance in series that you can replace these 2 resistors with. And then once I've done that, look what happens. Now I've got this resistance in series and this equivalent resistance, this resistor 1, whatever that is, I don't know what that is, whatever that is. And then those are obviously in parallel. They're connected on each side by just a wire, nothing in the way. So then I can combine those to make one that's just a equivalent resistance in parallel right here. And then all of a sudden, this first resistor is in series with that resistor that represents every other resistor in the circuit, right? This resistor now represents these 2, and these 2, and these 2, and these 3, and everything else. Add those together, and you have the total resistance of this circuit. This resistor represents the total overall resistance of this circuit. But it does take a lot of steps and a lot of calculation. And I would highly recommend that you do not try to skip steps. Every single circuit, draw it again. Draw a new circuit. Every single calculation, do it right then and there with that circuit. So with this circuit right underneath it, calculate the equivalent resistance for these in parallel, for these two in parallel, do those calculations, replace them up here, draw a new circuit. Do the calculations for these two in series, draw a new circuit, replace the resistor with the new one in series. Keep doing it until you're all the way down to the simplest circuit you can get. And then once you're there, if you know the voltage and the current, or the voltage and the resistance, you can calculate how much current is going to go through this total circuit. Once you know the current that's going through this resistor, then you can figure out that it's the same current through these two because they're in series. And then you can figure out that it splits between these two in parallel. And you know how that split works because we just did the math. And then you can figure out that it's saying this. Well, anyway, let's do an example and show you how it works. So here's a very simple example. We have a current coming. We have a current going out of the battery, going through a single resistor, and then splitting up and going on through two resistors in parallel, and then coming back to the battery, right? And we want to figure out what are the currents through everything. What's the current through this resistor? What's the current through this resistor? And the current through this resistor. And we'd also like to know the voltage across each resistor. We want to know everything everywhere. So we go ahead and get started by simplifying. We know that R2 and R3 are in parallel. So we go ahead and replace those two resistors with an equivalent parallel resistance. This is the calculation for that. 1 over R2 plus 1 over R3 equals 1 over R parallel. We calculate that, and then we invert it to get R parallel. And we replace this pair of resistors with a single resistor with this resistance 4.11 ohms. Now they don't draw the picture. You should. Right? But they don't. Just draw a new picture where we have one resistor here and one resistor here, and then it goes right back to the battery. And that one resistor on the right side is going to be 4.11 ohms. Then those two are going to be in series. So you add them together in series, R1 plus that RP, or R equivalent for parallel. You get 1 plus the 4.11, you get 5.11 ohms total resistance. And then you draw a new circuit, which is just the battery and the total resistance of the circuit back to the battery. And then that total resistance is going to be 5.11 ohms, and we use Ohm's law to calculate the current. So the total current going through the circuit is 2.35 amps. We also know, now that we know the total current is 2.35 amps, we can calculate the voltage across this resistor because the current comes out here, and the only way it can go is through that resistor. All the current coming out here is 2.35 amps. And when it hits this resistor, it all has to go through it. It has no choice. It has to go through these rapids. So
you
all.
gotta figure out the total before you figure out each second.
Yep. So once we figured out the total current, we know that all of it has to go through this resistor. When it gets here, the current can split. But when it goes through this resistor, it only has one path to follow, so it has to go through there. Current cannot disappear. It has to be conserved.
Now, whenever you figure out how much goes through the first one in series, now do you have to subtract that from what goes across the two in parallel, and then figure out them two?
No, because
separately?
the current doesn't get lost. Are you talking about voltage or current? I'm just talking
Current.
about. No, the current, you never do any subtraction or anything else. The current has to stay the same. Right? The current is flow of something. It's actually flow of charges. So if the charges flow through the resistor, they don't get lost in there anywhere.
Okay,
They have to keep going.
So whenever you figure out the current from the two in parallel on that
What gets lost, when it goes here, the current splits. Some of it goes this way, some of it goes this way. When it gets on the other side.
So you use the sum number that you figure out for the total,
Yep.
then you do it as a set in parallel to figure
Yep.
out each one.
Yep. So when it goes through this resistor, all the current goes through this resistor so we can calculate the voltage. Now voltage does drop. Voltage goes away because voltage is related to energy, and the energy in this circuit does go away. As the resistors heat up, energy leaves the circuit in the form of heat. So the energy in the circuit does go away, but the current does not. Okay?
That's your wattage, right?
No, the power is your watts, but the voltage is just volts.
Yes,
So-
the stuff dissipating would be your
The stuff dissipating is usually measured in watts because that's That's essentially energy per time. But in any case, to calculate how much voltage drop there is from one side of the resistor to the other, we use Ohm's law again. Current times resistance. We use the current of 2.35 amps times the resistance of this circuit. And we find out that we get 2.35 volts of voltage drop across that first resistor. But once we've dropped 2.35 volts, we only have 12 minus 2.35 volts left. Because we started with 12 volts and we dropped 2.35 volts. So we're only left with 9.65 volts on the other side of this resistor.
Yeah, that's where you subtract what it is.
And if you have 9.65 volts on this side of the resistor and 0 volts on this side, which is what we do have because it's connected to the negative end of the battery, then the total voltage drop across these two resistors is 9.65 volts. It's whatever's left. So the voltage drop from here to here and from here to here is 9.65. Then we can use that voltage and these resistances to calculate the current through each of these resistors. So we use that voltage and the resistors to calculate the current through resistor 2 and the current through resistor 3. They go ahead and do that. They use voltage 9.65, resistor 2 6 ohms, calculate the current through resistor 2, and then the 2.35 minus this will tell you whatever current's left, and that has to go through the other resistor, right? So essentially just kind of you're tracking currents and you're tracking voltages. Voltage, the total voltage it drops across all things has to add to the total voltage in the system. The currents have to be the same at the beginning as they were at the end. So when you leave the battery with a certain amount of current and you come back to that battery, you have to have the same current going back in because the current has to form a loop, right? It's to form a closed loop. And then they do some they calculate power in resistance 2, for example, by taking the current going through resistance 2 times the resistance 2. And so current squared times resistance equals power, and that's 15.5 watts. So you can calculate current, resistance, power, voltage, whatever you need, as long as you track things well and you know enough things to start with. And usually when you create a circuit, you know your voltage supply, so you know what your batteries are that you put in, or whatever you're using for power. You know your resistors that you put in. You know what all the components are when you wire up a circuit. What you usually don't know is exactly what's going to happen with the current and the voltage. So that's what we use these skills for. So here's a nice example of a circuit like this, the refrigerator, right? And it's actually very simplified. So the wires are quite a bit longer in a refrigerator, and they get really quite hot, actually, in many cases. So they actually have a fair amount of resistance. So they've actually represented the resistance in the wire with a little resistor here. And then you come in here and you have multiple things that are going in parallel. So this is the plug in the wall. That's what this little circle, the squiggly line means. That means an AC power source, so that's the plug in the wall. And then this comes up and it splits, and some of this current is going to go power the motor, and some of it's going to go power the flash, the bulb in the refrigerator, the light bulb, right? Which one of these resistors has the lower resistance, do you think? What's that?
I'm going to guess the fridge because it needs more, they want more current.
So remember, when you're in parallel, current splits and it wants to follow the path of least resistance. So you want most of your current to go where? Where is most of your current needed? It's actually in the pump down here, the motor. So they make their motors very low resistance, so the current will want to flow down here. And motors generally are fairly low resistance. Light bulbs can be low resistance or high resistance. It just kind of depends. But in a case where, in a case like this, we definitely make them high resistance, so that the power doesn't get drawn through here. We want all the power down here through the pump, right? So lower resistance, higher power, higher resistance, lower power when they're in parallel. It's the opposite when they're in series. But we don't want, when the light turns off, when the light burns out in our refrigerator, we don't want our motor to turn off, right? So we don't wire them in series. When I was a kid, they used to wire Christmas bulbs in series because it was cheaper. You used less wire, and the wire is the expensive part of Christmas lights. So they'd wire them in series, and whenever you lost one light bulb, your entire Christmas decoration would go off. You'd have to go out and figure out which one was off and which one blew, and usually it was fine because usually the light bulb would explode back then. They were cheap light bulbs too. So you just go look for the light bulb that was missing, and then you'd go replace it, and you were great. You were good to go. Nowadays, people got tired of that though, and it was in the '80s when people just got sick and tired of that, started demanding Christmas lights that wouldn't go out every time you lost a light bulb. And so now you can lose like 10, 15 light bulbs before the string gives out. But eventually it does give out because they still wire them in series sometimes, but only parts, a certain length of the thing in series, and then that one will be in parallel with the next length or whatever. Okay. Now that they are using LEDs for Christmas bulbs, they're...
They have the diodes and resistors built into them.
Yeah, but also since they draw so much less current, since an LED draws almost nothing. It draws very, very little current. So that means that they can make their wires out of something less than copper. Because copper is what you have to do if you're drawing current, because it doesn't melt when you draw a lot of current. And so you can make wires out of aluminum when you're making LED lights, which is much cheaper. Aluminum is very plentiful and very cheap compared to copper. It's also lighter. Okay, first section down in the books. Or was that the second section? No, first section. Man, we're a ways off from being done. Got 6 sections. We just barely got through the first one. All right, now electromotive force. Some of you noticed that there was an EMF problem in the last chapter's homework, and it was an accident by me. It could have also been that they put it in the wrong section because they usually try to put the problems by section. And I was in a hurry, so I wasn't checking problems with sections very well. Electromotive force is what we sometimes call EMF, and it is actually it's a misnomer, and it's kind of an antiquated phrase, but still used, particularly when we're using batteries. So the electromotive force is what people used to think. They used to think that voltage was a type of force that pushed electrons or pushed charges through the wire. And while that kind of, still is kind of true if you think about it in a certain way, it's not exactly true. And we know now that voltage is what we call potential, but it's more like it's a potential energy per unit charge is what it is. So it's more like energy than it is like force. And of course, energy can provide force. Energy does work. But anyway, the point being is that it's an old way of saying what the voltage is of a battery. The EMF of a battery is the voltage of a battery. So in particular, the EMF or the EMF of a voltage source is particularly the voltage when no current is flowing. So if you have a 12-volt battery, for example, some 12-volt batteries are actually designed. Many 12-volt batteries are designed to have 15 volts when they're not actually driving current. But the 12 volts is supposed to be the voltage when it's being used in a normal kind of way. So if you have a voltage monitor in your car of your battery, you'll often see that it's up around 15 instead of 12. And that's usually, you see it up around 15 when the battery's in good condition and you're not using it very much. Your air conditioning's not on, you're not driving a lot of current. That's because the battery's EMF is actually 15 volts. It's rated at 12 for usage, but its EMF is actually 15, closer to 15. And of course, 12-volt battery is not exactly 12 volts, and Neither is a 15-volt battery exactly 15 volts or anything else. These are approximate numbers. But why would it change as it started as current started drawing? Why would that change the voltage of the battery? Because the voltage of the battery is the source. Well, the reason is because the battery is part of the circuit. Remember that when a battery is connected to when it's connected to a circuit, like let's see here, I don't have a good. Oh, here we go. When a battery is connected to a circuit, it not only has whatever it's trying to power, which is the load resistance, we usually call that, but it also has itself to drive current through. And batteries themselves have resistance. Batteries are like little resistors, and that resistance changes as the battery gets warm, which it does when it's being used. That resistance increases. So when the battery is cold and it's not being used much, it has very low resistance. And hence, its voltage is actually higher. But when its resistance increases as it gets hot, there's a voltage drop across the battery. In other words, the battery loses some of its own voltage. It actually affects itself. So it has a voltage drop across the battery, so it goes from 15 volts across the battery when it's cold down to maybe 12 volts when it's being used. And the more load that you put on it, the more current you drive out of a battery or out of some source that has some limit to it, the more it drops. The more it heats up, the more that voltage drops, the less voltage there will be for the system, right? So that is the idea. This is one of the reasons that we talk about the electromotive force, is so that we can differentiate between the voltage that the voltage source has when it's not driving a current and when it is driving a current. So how do we do that? What we do is we represent the battery as the battery symbol. The battery symbol has a longer line on one side, the positive side, and a shorter line on the negative side. I always think of it as the shorter line being a negative sign and the longer line being a positive sign that's been taken apart and lined up together. It helps me remember. I had a hardest time remembering which side was which. Positive side's the bigger side, negative side is the smaller side because it's just a negative side. But then next to it we put a resistance, which is usually a little r instead of a big R. Notice that we've used big R for resistors so far. Little r is for internal resistance of a power source. So if you have a power source, that little r next to the power source symbol will be the internal resistance of that power source. And oftentimes there's a circle put around that or a square or something to represent that it is a combined object. Then the voltage across this battery is going to be equal to the EMF of the battery, which is the voltage across the battery when it's cold and not driving current, minus the current that it's driving times its internal resistance. Because that is the voltage drop across the battery right there. So if you take the total EMF and subtract off the voltage across the battery when it's driving a current, you will get the voltage across the battery, or the voltage that the battery can provide for the circuit. So that's the equation that you needed in that problem we were looking at in the last chapter's homework. Here they kind of show how a battery, a simple lead acid battery works, where you put lead and lead oxide in a battery. Lead goes on the anode, which is the negative side. Lead oxide goes on the cathode, which is the positive side. And it turns out that, chemically speaking, these things have an electron affinity, you could think of it as, right? Whereas the lead really wants to be negative, the lead oxide really wants to be positive. So then in the acid, you get ions flowing. You get ions going from one to the other and back and forth, and that's a flow of current. And it creates a very positive lead oxide cathode and a very negative lead anode, and then you have a potential. The more and more charge that builds up on those two things, the more and more potential you get. And you can drive that potential, you can drive that process by connecting it to something that has a potential difference, like a battery charger. So you can connect it to a battery charger and you can drive that process and charge the battery up to its maximum EMF. And the more of these things that you have, the more voltage you can get. And so if you just have one cathode and one anode, the EMF of a battery like that is 2 volts. So if you have 6 of them, you can get up to 12. If you have 8 of them, you can get to 16, you know, nominally the ideal thing, and so on and so forth. It's either, it might be 1.5. I think it's actually 1.5. What is the EMF of a AA battery? So a AA battery is not actually a lead acid battery. They used to be lead acid batteries, but they're not anymore. Now they're alkaline, which is something they've been for a few decades now. And the voltage is, oh, here it is. Oh, so the EMF is 1.5 volts. So it's 1.5. So if you want a 12 volt battery, you have to have 8 of these. If you want a 15 volt battery, you have to have 10 of these, right? And so on and so forth. So the EMF is 1.5 for lead. Now for different materials, it's different amounts. For different materials, cathodes, for different acid mixtures, lithium ion is different. You know, every different thing is different. Has different amounts of voltage that it can build up to. So batteries are decidedly variable. So this V that you get from taking the EMF and subtracting off the voltage drop across the battery, we call that the terminal voltage. That's the voltage actually across the battery in the circuit. And if you have a load in your circuit and you want to calculate the circuit, so this is what it looks like when you have that load. If you have the load in the circuit and you want to calculate the current, you have to add the load resistance and the internal resistance of the battery because they are in series, right? So you add the total resistance in the circuit, which is the load resistance, add that to the resistance of the battery in series, and then you take the EMF of the battery, which is the voltage without any current, divided by those resistors, and you will get the current that this battery will drive through the circuit. So another useful equation. So here we have a battery that's a 12 volt EMF battery. So that's the amount of voltage it has when it's not driving current. Has an internal resistance of 0.1 ohms. So that's the little r. We want to calculate its terminal voltage when it's connected to a 10 ohm load. Well, that's this equation right here. EMF over resistance load plus internal resistance. Turns out to be 1.188 amps. If you want to know the terminal voltage, then you plug little r and the current that we just calculated into this equation, get the terminal voltage of 11.9. So with that much load, with 10 ohms of load, the load was 10 ohms right here, 10 ohm load. With a 10 ohm load, you get 11.9 volts of potential difference across the circuit instead of the 12 that the battery supposedly was able to provide. It drops down slightly. For B, in part B, they want to do the same thing for a load of 0.5 ohms. For a 0.5 ohm, it's a terminal voltage. Terminal voltage for a 0.5 ohm load, we need to calculate the current first to know this. So we calculate the current, we get 20 amps of current, and then we do the EMF minus the current times the internal resistance, plug those numbers in, and we get 10 volts. We get a bigger drop. Why is it a bigger drop? What happens between between part A and part B? Resistance went down, and what did that do to the current? It went up. So in the second situation, where we had a lower resistance, the battery pushed more current through that load. The battery was doing more work, essentially. That's really what it comes down to, is the battery has to do more work, and so when it pushes more current through, it can't provide the same amount of voltage. And that's just life in the real world. So then we calculate the power dissipated. Well, power dissipated is going to be equal to I squared times R, or V squared over R, whatever you're going to use. Just make sure you get your numbers right. If you use V squared over R, you have to use the terminal voltage. You can't use the EMF. You have to use the terminal voltage because that's the actual voltage being supplied by the battery when it's driving at that particular current. But whatever equation you use, you're going to get 200 watts of power dissipated. Right? So as you have those bigger currents, you get bigger power dissipated. In the last one, they want us to in part D, if the internal resistance grows to 0.5 ohms, find the current, terminal voltage, and power dissipated. So what if it increases to 0.5 ohms? And batteries do increase their internal voltage with heat, or their internal resistance. As batteries heat up, their internal resistance increases. So it's not just constant. So what if it increases to 0.5 ohms? Right? If it increases to 0.5 ohms, then we have a different current because we have a different internal resistance. So it becomes 12 volts over 1 ohm now of load plus resistance. And we get 12 amps. Notice that before we had 20 amps with the only 0.1 ohms of internal resistance. We got more current out. In this case, we got less current out because the internal resistance increased. So not only, well, let's go to the next thing. So the next thing is to calculate the terminal voltage. Terminal voltage is EMF minus I times internal resistance. So that actually gives us 6 volts. So the battery voltage has gone way down as it heats up. And this happens a lot with batteries. As batteries heat up, their terminal voltage drops off a roof. And then they can't provide the current that they were before. So not only are they cranking out a fair amount of current, but they're cranking out so much current that they are heating up and they can no longer provide the voltage that they did before. They're losing voltage inside the battery. And so the amount of power dissipated goes way down. So if the thing that if you're trying to power a vacuum, for example, and you're powering a vacuum using a battery, and your battery starts heating up, eventually you may not even provide enough power for the vacuum to work, or the light to work, or whatever else. And this is what happens is batteries die. When batteries are dying, their internal resistance is increasing because of the heat that they've had going on in them. The heat inside the battery, really what it does is it actually changes the chemical composition inside the battery. It changes the chemistry of the acid. And it degrades it so that it doesn't do what it's supposed to do. And as it does that, then the internal resistance changes, voltage starts dropping, current drops because voltage is dropping, and then eventually you don't have enough power in the system to light the light bulb or to run the power grid. And then you have to replace the batteries or recharge the batteries or whatever else. So, with rechargeable batteries, they're sealed up and made of a material that doesn't degrade very well. So as a rechargeable battery dies, what's happening is that all the charge is going from all the current is going from the cathode to the anode, and eventually it just runs out of charge. And eventually the anode and cathode are backwards. One of them is positively charged when it should be negative, the other one's negative when it should be positive. So you put that in a charger and it reverses it again, reverses the process by driving the current the other way, and then you can use it again. But with normal batteries, usually what happens is that discharge thing happens, but at the same time you're also heating the battery possibly, and eventually you just can't use it anymore. In some batteries you can reverse the process, some you can't do so safely, so you don't do it. And that's actually one way that a battery charger knows if a battery can be recharged. It actually, a good battery charger will test the internal resistance of the battery before it charges it. And if the internal resistance of the battery is high, it knows that it's either A, not a battery that's supposed to be recharged, or B, it's a battery that's dying, so it can't recharge it. So the first thing a battery charger does is drives a little current through it at a constant voltage, tests the internal resistance of the battery. That's exactly how they test batteries for whether they're good or bad, as they look at the internal resistance. If internal resistance is high, it's dead. And recycling batteries is actually fairly easy to do in theory. All you really need to do is purify the materials the battery is made out of, which usually involves dismantling the battery, taking out the anode and the cathode. If it's a lead acid battery, you melt down those metals to make lead again. And then you have lead oxide you put through a solution to create lead again. And you have lead oxide mixed with acids and all kinds of other things. And then you just create new anodes, and then you take all the acids out of the battery and you put them through a chemical process, and you separate out the impurities and make the acid again that you need, and put it all back together. In theory, it's a simple thing. In practice, it's messy, it's dangerous. So anyway. Batteries in series. If you put two batteries in series, you get two resistances, internal resistances in series that you're just going to add together. So the more batteries you have in series, the more overall internal resistance you're going to have. However, if you put them in series, you also add the voltages as long as you line them up in the right direction. If you line them up opposite, it's like 5 volts minus 5 volts and you get 0. But if you line them up in series so that the positives point in the same direction, negatives point in the same direction, you actually add up the voltages. So putting batteries in series allows you to increase voltage even though you're increasing your internal resistance. But it can be a great advantage for many reasons. And this is exactly how they make batteries with higher voltages. You have those multiple cells within the batteries, and then those cells are connected in series so that you increase the voltage. And they're showing that here. These are simple batteries in plastic cups with acid and lead. You can make batteries with all kinds of things. It doesn't even take that much acid, really. However, batteries in parallel do something different entirely. When you put batteries in parallel, of course, you have resistors in parallel. And what happens to the resistance when they're in parallel?
It's got to be lower than
Yeah, it lowers the internal resistance. And these aren't exactly in parallel because the batteries are here, but they behave as if they are in parallel. Because batteries, this battery here just increases voltage. It doesn't do anything else. It doesn't branch the current off anywhere. So these behave as if they're in parallel. But when you have the batteries themselves in parallel, the voltage actually doesn't change if they're the same voltage. If you've got them lined up and they're, the positives on one end, the negatives on the other end like this, it doesn't change the voltage. It keeps the voltage difference the same across the batteries. But what it does give you is, what's that?
it increases their ability.
Their ability to provide current. So each battery is like a tank of current. And it can provide so much current. But if you put two tanks side by side and then provide current side by side, you can provide twice as much current. So it increases the amount of current in a linear fashion. So your current all of a sudden doubles when you do this. But your resistance, your internal resistance, goes down.
So if you have batteries connected in parallel, while it won't provide more power, it will provide power as well.
The first statement is not true, the second one is. It can provide more power because the internal resistance goes down. So as this kind of a battery, as batteries are placed in parallel, the internal resistance goes down, 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 down.
So it won't provide
Then as it provides current, its voltage doesn't drop as much. So it can provide more current without dropping its voltage as much. So it can provide more power. It provides more power by keeping its voltage higher while it's providing current. But also it provides more power by providing more current, right? So yes, it can do both. So this definitely has its advantages too, except that you can't increase your voltage in this. So it'll just keep it at a higher rate longer as you're providing current. So they each have their advantages and disadvantages. And oftentimes in a circuit you will have batteries that are connected sometimes in parallel, sometimes in series, and sometimes a little bit of each, a little bit of, kind of in between somewhere. They're not really one or the other, but they're put in the circuit in a specific place to boost the current or to boost the voltage or whatever. And that's not uncommon at all. Excuse me. All right. So, if you're trying to light up a light bulb in series like this, light bulbs, usually what you have to do to light up a light bulb is you have to provide a certain amount of current through the light bulb. But since the light bulb has a resistance, to provide a certain amount of current, you need a certain amount of voltage because the resistance is fixed. And so the idea then is to decide whether or not you need to put them in series or in parallel. If your batteries can provide enough current on their own, if one battery can provide enough current on its own to light the light bulb, but cannot provide enough voltage on its own to light up the light bulb, then you put them in series, and it will light up the light bulb. You put it in series until you get enough voltage to light up the light bulb. However, if your batteries have enough voltage to light up the light bulb, but not enough current, then you put them in parallel. And if they don't have either, they don't have enough of either, you put a bunch of them in series, and then you put those stacks of batteries in series in parallel, right? And there are flashlights and other devices that are like that. Particularly, I'm thinking of boom boxes back in the 80s. Back in the 80s, the big craze was to have a boom box, right? You've probably heard of them or seen them. But they really were quite a crazy thing. My friend had one that was just incredible. I could not believe it. And they were, I mean, these are mild. My goodness, the one that my friend had was so intense. It was just humongous. He was a big break dancer. It was kind of like this, but probably a little bit bigger. Probably more like that. And there are just hundreds of companies popping up everywhere making these things. You know, nowadays when you go get, you know, some kind of stereo component, there are quite a few companies out there. If you're talking about like companies that are reputable, there's maybe 4 or 5 companies out there that are reputable. There's a few more that are cheap coming from who knows where. But back then there were just companies popping up everywhere making these things. And they were all battery powered. And these, I mean, this thing was probably 3 feet long and probably 2 feet high. I mean, it was so big it took 2 people to carry it sometimes. And then it would have just dozens of batteries in it. Half of this thing was size D batteries. And you'd put in like 36 size D batteries and it would last you like one day. So you're paying like $5 a day. Batteries were cheaper back then. You're paying $5 or $10 a day just to run your boombox, and people would run them all day. And so, but it was hugely popular. Everybody'd set up their boombox in a big piece of cardboard and pretend to be a breakdancer. You know, breakdancing was huge where I grew up because I grew up, you know, not 20 miles from Oakland where it was invented. And you know, MC Hammer was big on the scene at the time in California. Anyway, he became bigger in the nation later in the world. But other, you know, there were all kinds of rap artists, and of course Michael Jackson was a big deal back then, and all these people. Everybody had a boombox with their tape players and their equalizers. It was just so goofy. It was, I mean, it was cool. I mean, there's no question it was cool back then. But it was still goofy. Looking back on it, they often call them ghetto box. You know, that's kind of not. Oh, here's one with a record player built in. That's just sweet. Gotta love it. Anyway, the boom box was a great big deal.
So I'm guessing that one had both.
It had both parallel and series because it had to provide enough voltage, which took about 12 volts. So you had to have 8 batteries lined up in series. But the current that it drew when it was driving those big speakers, my goodness.
32 batteries, you had 8 in series.
And 4 sets of 8, yeah, 4 sets of 8 in
And
series.
then you had 4 sets of batteries
In parallel, yep.
That's
Yeah, it was insane. And you know, that many batteries, that many size D batteries gets heavy. It's really heavy.
And now you can take a little Bose thing that's this big and make better sound.
Oh yeah.
Just as loud.
Well, heck, your cell phone makes better sound than these things did.
You know,
If you have a good cell phone. I mean, I think there's maybe 3 or 4 phones out there that have really good internal sound that it would beat these. I mean, maybe not for volume, but for
but for
sound
clarity
quality.
and-
Yeah. And some of them are pretty loud. I mean, is it Samsung that makes one that uses the Beats speakers in it or something?
Yeah.
And it's pretty loud, actually. So it's kind of crazy. But, yeah. So anyway, batteries in series, batteries in parallel. Gotta love it. Oh, you gotta love the fish that have this ability, right? Fish, sharks, platypus, echidnas. What's an echidna? An anteater. They actually have potential differences inside their bodies. We all do, actually. Our bodies are just huge batteries. If you've ever seen the movie The Matrix, they turn humans into batteries for robots, right? But all life has potential differences inside the body everywhere. But some animals use it a little more directly than humans do. Sharks actually detect changes in electric field, changes in potential up around their nose. Very, very minute changes. This is why they say if you're ever bitten by a shark, punch them in the nose. They're extremely sensitive and they lose all sense of everything if they get hit in the nose. So if you hit a shark in the nose hard enough, it's very likely they'll let go of you and just kind of be dazed. You know, if you have that sense of self enough, being devoured by a shark to punch them in the nose. Most sharks bite on the lower leg, so you might have a chance to do something. But this is the same with eels. Eels create a potential difference from head to tail and use that to shock their victims, you know.
I think we should go to the Bahamas and experiment with this on Shark Tank.
Go to San Francisco. Go to the San Francisco Bay. They have real sharks there. They have the great whites that are like 18 feet long that eat boats whole. Like they cut open great sharks, great white sharks in the San Francisco Bay, and they've found like entire tiger sharks inside of this great white.
But I don't want Packer to get hurt.
And then the really funny thing is that orcas, the killer whale, they do not attack big fish, except for great whites.
Yeah.
They like have this vendetta against great whites. If they see a great white, they swarm it and they kill it. It's mostly, I think, because they're protecting their babies. Because
I think they kill like all big sharks there.
they'll kill most big sharks because they're predators for their babies. But great whites in particular, great whites are easier to see, I'd imagine, underwater. But they just, anytime there's a great white near a pod of orcas, the great white is dead. Because orcas don't feed on them. They just destroy them. They'll eat the liver. Apparently the liver tastes good.
I think what are they? They're like 60% of their body.
Yeah, 60% of their body is their liver. Because that's how they stay afloat, actually. That's how they create their buoyancy, is by their liver. Sharks are kind of funny. If they stop swimming, they can't float. No.
They don't have a
No,
buoyancy.
if they stop swimming, they float and they die. They can't adjust their buoyancy using their body. They have to swim to adjust their buoyancy. Their liver is the only thing that is buoyant in their body, but it's so buoyant that they just float to the top if they stop swimming. And then they die because they can't breathe.
So if you can get a shark to stop in its tracks.
Yeah, good luck.
Whoa, big fella.
Massive flashlight.
Oh, so funny. Solar cells. I actually have the equipment to make solar cells. You use copper foil. Maybe we should do that for our lab this week.
Okay.
You use copper foil and you heat it up until it oxidizes. And then and it like turns blue or something. And then you put that inside of salt water. I think you sand one side of it so that you have copper.
Yeah, the solar cells are getting really efficient now.
Oh yeah, much more efficient than they've been. I mean, they're up above 12%. That's really efficient when you consider that a hybrid coal gas-fired plant is like around 50 or something percent efficient and way cheaper. But yeah, solar cells are not the way to make solar energy. If you want to capture solar energy, you just reflect all the light onto a tower filled with liquid sodium. You heat the liquid sodium, you use the liquid sodium to turn a turbine, and then you use the liquid sodium to actually heat water to make water into steam, then you use the steam to turn a turbine. It's much more efficient that way. But anyway, solar cells are an interesting device that when they're hit by light, you get this effect called the photoelectric effect, which was one of the papers that Einstein wrote in 1905. Albert Einstein wrote 5 papers in 1905, each one of them absolutely groundbreaking. The least impressive of them was his description of the photoelectric effect. He was able to tell the world why the photoelectric effect worked in this paper. But that's the one he got the Nobel Prize for, because that's the only one that the Nobel Prize Committee can understand. So it was his least impressive. His most impressive paper, which was on the special theory of relativity, he never got a Nobel Prize for, never got any real prize for it, but it was the most important and the most amazing, it changed science more than anything else.
So maybe Isaac Newton's gravity?
What's that?
Is it maybe Isaac Newton's gravity?
No, it changed it more than Isaac Newton's gravity, more by far. People may not have said that 50 years ago, but this year, after what's happened the past few years, definitely. Einstein changed the world, I think, much more than Newton did.
Yeah, but we're pretty well done with big physics.
Oh, no.
You don't think
No, there was a new one just a few months ago, just a couple weeks ago, a few weeks ago, I don't know. What was it? It was they. I can't remember what they were able to detect just a little while ago, using gravitational or understanding of gravitational waves. They were able to detect something about black holes that was just amazing. And I mean, we're just learning about black holes. I mean, we've always known that they existed. We've been able to detect them in the past, but what we knew about them was almost nothing. Now we're starting to realize that they play a huge role in the universe. And the things that we're learning about the universe that we thought we knew a lot about the universe, now we're learning that we almost know nothing about it. But the things we're learning new about it are so interesting and different that it's turning science on its head just about every other few months. It's just incredible. We're not done yet. I think personally that in the next couple of generations, we're on the verge of a Star Trekian type revolution in science. Like, I think in 100 years, we will be where Star Trek predicted we would be. I think we'll be traveling to different stars because we'll understand space so much better. And traveling to stars right now.
Enemies.
Traveling to a star right now is absolutely impossible. Absolutely impossible with what we know and what we can do right now. We have to make incredible changes to our understanding and incredible changes to our technology that we can't even imagine at this point. But Star Trek took care of that by just saying, well, we can't imagine it, so we'll just make up something that, will not likely ever be true. We'll make up something that bridges that gap, and then we'll just go from there. The Star Trek universe started 200 years after. I mean, it was invented. Star Trek was invented back in the '60s by Gene Roddenberry, and his first Star Trek show takes place 200 years after the '60s. So he put a 200-year gap in and said, in the next more like 250 years. In the next 250 years, maybe we'll figure out something that will help us to do these things. And I don't know what it's going to be, and I'm not going to try to explain it. I'm just going to give it a name, and I'm going to go from there. The name that he gave it was warp technology. And we really have, there's nothing really to explain what it is, except that it fixes all the problems that we would have going to a star. Now, it just fixes all those things somehow. It's brilliant, and I think that we are on the verge of that. I think that we're on the verge of understanding enough about space that within the next generation or two, we will figure out a way to do it. But it's exciting. There's just so many cool things that we're learning. And those things are not going to become part of the public knowledge for quite a while because it's just too far beyond what people understand. It's way far beyond the education of this generation. In order for it to really become part of the general knowledge, we're going to have to change the way we educate as well. Everybody who is born will have to take calculus eventually in order to just survive in the world. Because soon, technology in this world would be so far beyond our human experience that you won't even be able to get up and eat breakfast without a basic understanding of calculus. It just won't happen. And I mean, there will be no survival for those who are not willing to learn, unfortunately. And it's just the way the human race is going. There's this huge divide now with education. The people who are educated at calculus and above are climbing. The people who are calculus and below are diving. towards obscurity, you know. And it's economic, it's social, everything about it is splitting, you know. And it's eventually going to be that way. Eventually, people who do not have a high level of technical understanding are going to struggle in this world. It's going to be, unfortunately, kind of bad. So, I don't think it's a good thing necessarily. It's exciting for me because I enjoy science and technology and everything. But I think it's sad for people that spend all their life studying music, for example, because generally they don't try to get something technical in their education. And that will, I think, hurt them in the future. But, you know, maybe I'm wrong. Hopefully I'm wrong. I don't.
That movie where a guy was put in a pod and woke up like 300 years later.
I don't know. There's been like 50 movies like that. But
And
which one?
and the whole population of the world was like really dumb.
There's been a few like that too. I'm trying to remember one in particular.
Yeah.
There's, of course, The Time Machine.
Oh.
That's the classic one, the first one that was ever written like that. But
For him and like some waitress.
no, I don't know that
And
one.
it makes him president.
Because he's not dumb.
Yeah.
That's pretty much how we do it now. You're not stupid. You can be president. You're not really smart either, but when was the last time we had a truly intelligent president? It's kind of hard to really think back to somebody who's actually done something truly amazing for our country and actually accomplished something. You know, Barack Obama really did try. And he had some good ideas, but he was really stupid in the way he went about it. He just figured he could just not work with Congress. He figured I'll just ignore half of Congress that's not in my party and just try to get things done that way. If he had just compromised a little bit and made friends a little bit with the other party, he would have been a phenomenal president. He would have done great
Yeah, but
things.
Look at how big a failure his healthcare law was.
Right, and that's why he failed, is because he didn't look at both sides. He didn't say, what do both sides of the political spectrum have to add to this? Because, you know, Republicans aren't stupid and Democrats aren't stupid. If you bring them together and make them compromise, they actually make smart bills together. Because the stupid parts of the Republican kind of balance out the stupid parts of the Democrats. And then you get something in the middle that actually works. It's usually the middle that works, not the extreme ends. But he just wanted to be on extreme one end, and we have presidents that do that all the time. But the ones that are successful, Bill Clinton actually passed a lot of laws, and some of them were really good and did a lot of good for the country. I didn't like him personally, but he knew how to compromise. And our presidents since him have struggled with that. Struggled. And I give,
I think the best thing Trump has done so far is the tax law, and then making the one where for every one due you make, you have to get rid of 2 over.
well, and in Trump's defense, many people hate Donald Trump, and I did not vote for him. I did not vote at all. I couldn't in good conscience. But in his defense of many people that think he's crazy and everything else, he is trying to compromise. He has some strange ideas. I think building a wall on the Mexican border is just dumb. But increasing security is not dumb.
Between Mexico and Panama.
Well, sure. That's like 100 miles.
Yeah.
The border between Mexico and the United States is the biggest border in the world. There's no bigger border anywhere.
Russia and Europe.
No, well, that's Russia and Europe. That's 25 different countries. But between Russia and China is probably the second biggest one, between Siberia and China. But I think the Mexico-United States one is the biggest one in the world.
Wouldn't the United States-Canadian border be bigger?
Yeah, but that doesn't really count because Canadians are just Northern Americans. There's nothing to fear from them except hockey. They might invade us with hockey, eh? No, Canada is not any kind of threat to anybody. They're so mild-mannered and so civilized. They're like, if Canada invaded the United States, they'd probably give us, something that we needed. They'd probably give us some sanity.
And my dilute it with a little bit of socialism.
What's that?
And dilute the sanity with socialism.
Maybe. Yeah, they do have a fair amount of socialism in Canada, but anyway, so 21.3 is Kirchhoff's rules. I'm going to save this for next time because it is a big deal. And the last, these last 4 sections are all related and not really all that challenging after 21.3. 21.3 is a big deal. So we'll save that for Thursday. The problem with the homework this time is that many of the questions at the beginning of the homework are actually from the end of the chapter. So they're definitely not in any kind of order. I know that I've done that in the past. I don't know if I can change the order. I might be able to.
Okay. So I had some questions. And they were all like,
Change, withdraw. I don't think I can change the order
We need
necessarily.
a 20 question rule.
What's that?
double already established.
Yeah.
So what you need to do is you need to kind of skip around and find the ones that make sense to you from what we've learned so far, but avoid the ones that are maybe a little too hard, like the first 2, for example, are Kirchhoff's junction rule and Kirchhoff's loop rule. We haven't done those yet. So make sure that you don't try to do them necessarily in order. I'm going to go ahead and stop this recording.